All right, let's do this. So, I'm excited. This is my first video using this new pen that I got. My old one was janky, was causing me problems. You don't care. All right, here we go. So, today we're going to do conservation of energy. All right. And so conceptually, I guess there's not a ton here that's new from last year, but we're definitely going to ramp up the difficulty as far as the problems that we're solving. All right. So, in this video, we will be focusing specifically on conservation of energy problems where we don't need to worry about elastic potential energy. All right, we'll do that in the next chunk. All right, so um, when we deal with energy, sometimes a force can do work on an object and that'll change the energy in some way. Okay, and so to figure out how work done on an object changes the energy, we have to decide what type of force it is. And there are two types of energy that we need to worry about, or two types of forces rather. There are conservative and non-conservative forces. All right, so conservative forces are forces that are responsible for a form of energy. Okay, so gravity is a conservative force because it is responsible for gravitational potential energy. Okay. The force of a spring or a rubber band or something like that is called conservative because it is responsible for elastic potential energy. It's outside the scope of this course, but if we ever dealt with electric forces or chemical forces, those would also be deemed conservative. Okay. So conservative forces are important because they don't change the total energy. Okay. Conservative forces are important because they don't change the total energy. All right. Non-conservative forces are basically anything that's not conservative. So if there isn't a form of potential energy associated with it, then it is non-conservative. Okay. A little bit of notation just so that you know. Oh no, I'm going to get to that in a later video. So hold off on that. All right. So if a force has a form of potential energy associated with it, it's conservative. If it does not have a form of potential energy associated with it, it is non-conservative. Okay. So for us, non-conservative forces are going to be, oops, I wanted that to be red. Non-conservative forces are going to be things like friction, normal force, forces like Roy or Sally, okay, that kind of thing. All right, those are going to be non-conservative forces. All right. So then the question, I guess, obviously, maybe not obviously, but a question you might ask is, well, why don't we just come up with like frictional potential energy and then make friction conservative? And you can't do that because in order for a force to be conservative, it has to meet this condition. A force is only conservative if the work done by the force between 2 points doesn't depend on the path followed. Okay. So, for example, if I take a box and slide it from here to here, friction's going to do some amount of work. But if I slide it from here and then to here, the amount of work done by friction will be way more, which hopefully is sort of intuitive to you, right? Because you're going to sort of spend more time, there's sort of more distance for friction to work against you, okay? Because friction always opposes the motion, okay? Another way this is often said is a force is conservative if the work done on any closed path is zero. So if I take an object and move it from here to here, if the work done in going from starting point back to where I started is zero, then it's conservative. Okay. So in both cases, friction doesn't satisfy that condition. Okay. But it turns out gravity and springs do. Okay. So here's an example here. I'm not going to go through the calculations. You can do these on your own time, and I'm confident that you will. It is actually a good idea to at least think it out. So imagine a slide on a playground or something. All right. All right. And Sally's a little bit a little bit shy, not shy, but cautious, we'll say. All right. So she is at the top of the slide. On Monday, she's afraid to go down the slide because, ooh, scary fast. So she climbs down the ladder and then walks across to the end of the slide and ends up here. Okay. And she calculates the work done by gravity on Monday. All right. Tuesday, she's feeling a little bit more gutsy and she goes actually down the slide and she again calculates the work done by gravity. And it turns out that both days gravity does the same amount of work. Okay. And a big part of this has to do with sort of how you calculate work and the fact that gravity is always directed downwards means that all that really matters is her vertical displacement. Okay, and no matter what, on both days, her vertical displacement is the same. Okay, so I don't want to get too bogged down with it. That's the difference between conservative and non-conservative force. All right, so how does all of this matter? So when a force does work, it's going to change the energy in some way. We learned this last chapter. In order for a force to do work, the object has to be moving, and the direction of the motion can't be perpendicular to the direction of the force. Work is always negative if the force works against the displacement in some fashion, okay? Now, conservative forces are important because, as I said, I think I alluded to this a minute ago, conservative forces, oops, that's not what I wanted to do. Conservative forces do not change the total energy, okay? So conservative forces don't change the total energy, okay? All they do is they convert potential energy to some other form of energy. Here I wrote kinetic energy, but it could be any other form of energy, okay? So when I drop my pen, I'm converting gravitational potential energy to kinetic energy. If I put it on a spring, now I'm converting gravitational potential energy to elastic potential energy. All right. Conservative forces only convert energy from one form to another, but never change the total energy. All right. Non-conservative forces are important because they will change your total energy. All right. And when we get to the next chapter, we're going to learn that the work done by non-conservative forces is equal to our change in total energy. Okay. And we're actually going to modify that a little bit this year because total energy doesn't, how do I want to say this? Total energy includes thermal energy, which we don't usually count. So this is actually bad notation, what I use in honors. And we're going to write this as change in mechanical energy. Okay, what do I mean by mechanical energy? Well, that just means kinetic energy plus potential energy. Okay, total energy would be both forms of mechanical energy plus thermal energy, in other words, heat. Okay, so when I ran through this in honors, I never really talked about heat energy. Okay, and honestly, it comes up very, very rarely, even in AP physics. So anyway, we'll talk about that more next unit. So, I've totally gone off on a tangent here. So, here's the deal. Conservative forces don't change total energy, and non-conservative forces only change the total energy if they do work. Okay? So this unit, we're going to do conservation of energy problems. And conservation of energy problems are as follows. If the only forces doing work on an object are conservative, then the total energy, mechanical energy, I should say, stays the same. Okay? If the only forces doing work on an object are conservative, then the total energy stays the same. So if we go back to Sally going down the slide, what forces act on her? Well, there's gravity pulling her down, but that's conservative. That's not going to change her energy. And normal force. Oh, but the normal force is perpendicular to the displacement. So even though the normal force is non-conservative, it doesn't do work, and so it doesn't change her total energy. Okay? So that's going to be the deal of this section. We're going to learn about how to solve problems in which the only forces doing work are conservative forces. All right? I don't like this slide. Yep, I'm going to just delete that. I should have done that before. All right, so as long as the only forces doing work on an object are conservative, the total energy stays the same. Again, every time I say total energy, I really mean mechanical energy. All right, so what does that mean? So suppose we've got a conservation of energy problem where our total energy, our mechanical energy doesn't change. Okay, so suppose we've got a problem where our mechanical energy at point A is equal to our mechanical energy at point B. So we did a ton of these problems in honors physics. They're the roller coaster problems, right? So suppose I've got a roller coaster, and here's point A, and here's point B, okay? So what that means is there's going to be height at point A and velocity at point A, and then height at point B and velocity at point B, right? So okay, so what would be true if the mechanical energy at point A is equal to the mechanical energy at point B? Well, let's see, I'm going to write it out again. So mechanical energy at A equals mechanical energy at B. That means that the gravitational potential energy at A plus the kinetic energy at A equals gravitational potential energy at B plus kinetic energy at B. Okay? All right, well, that means mass times 9.8 times the height at A plus 1/2 m times the velocity at A squared. Oops. Equals mass times g times height at B plus 1/2 m times the velocity at B squared. Notice I could factor out m on all of these, right? Divide the whole thing, both sides of the equation by m, and you get g times the height at A plus 1/2 the velocity at A squared equals g times the height at B plus 1/2 the velocity at B squared, right? So the standard honors physics problem was I would give you, so there's 4 variables here, right? 2 heights, 2 velocities, and I'd always give you 3 of them, and then you'd find the missing one, okay? But notice that for this to work, you have to know 3 of those 4 variables to find the missing one, right? So let's do some problems like that, right? So we did a bunch of these, right? Like, I don't even think I need to do this, but right? So if I give you height at A and velocity at A and height at B, then you can find the velocity at B, okay? So that's what we're gonna do, but there's an add-on, all right? So here we go. All right, so here we've got Roy Mega Colossal Land, all right? There's a new roller coaster there, and it's completely frictionless, so no non-conservative forces doing work. And no seatbelt. Ooh. All right. So we've got a circular loop here. So here, let me, I guess, kind of draw out the path. Do this in, oh, I don't know, how about what color is going to show up here? Green. So you're going to start here at the top of the hill, and then you're going to go down and around the loop, and then like this. Okay. So question A says, what is the velocity at the top of this hill in order to make it around the loop? Find the velocity with which he must go over the top of the first hill, which is 35 meters tall, in order to make it around the loop without falling out of the ride. Okay, so let's see if we can kind of figure out what's going on here. All right, so here's our roller coaster. It's weirding me out that it's going from right to left instead of the other way around. All right, and so here's the top of the first hill. We'll call this point A. And what we know is the height there is 35 meters. And the question wants to know, what does the velocity A have to be? And our goal is we need to make it all the way around the loop. So if we're in danger, our danger point is going to be up here at point B, right? Well, let's see. The problem told us that the loop, the loop has a radius of 15 meters. So if we go down here and we go, whoa, why is it doing that to me? That's annoying. Ooh, I've never seen that happen before. There we go. So if this is 15 meters and this is 15 meters, then that means the height at point B is 15 plus 15, or 30 meters. All right? But the problem is I don't know what the velocity at B is either. So I have too many unknowns, don't I? Okay? So the fact that I'm given information about one point and asked for information about another point is a clue that I'm going to do this using work and or energy, okay? But in order to do this, like I said, I need to know one more piece of information. We're looking for the velocity at A. That means there must be a way to find the velocity at point B, okay? So to figure out what that is, we got to jump back a chapter, okay? So one of the things we learned was that if you have a circular path, in order to make it around the loop, you have to have a normal force, right? So the idea is, as I go around in the circle here, we need a downward centripetal force. Well, gravity is already pulling us down. And we also need to make sure that we've got a normal force, right? And so sort of your breaking point occurs when your normal force is 0. Okay, that's like our breaking point. If the normal force is anything less than 0, right? I guess in that case it would mean not pushing down, right? Then that's when we're going to run into trouble. Okay, so what that means is at point B, what we have to have true is our centripetal force has to be at least as big as the force of gravity. So mv squared over r has to be at least as big as mg. Cancel the m's and you solve and you get that v squared has to be at least as big as g times r. Okay, and we can plug in our numbers and figure out what that is. And what you'll figure out is that v squared is at least, remember, we know our radius is 15 meters, right? This turns out to be 147 meters squared per second squared if you're keeping track of your units, or the velocity has to be at least, if you square root both sides, you get 12.1 meters per second at point B. Oh, that's the velocity at point B. So this velocity has to be 12.1 meters per second. And now we can do conservation of energy and find the velocity at point A. Okay, so let's try that. So let me clear up the board here a little bit. Why don't we do one of these? Whoa. Sorry, bear with me here while I clean up my screen a little bit. Incidentally, this calculation we just did here, we did a ton of these in circular motion, so hopefully that's, oh no! Hopefully that's at least familiar. All right, so going back to this guy, boom, boom, here's our velocity at B. So the total energy at these 2 points have to be equal. So if we solve this, we get, sorry, mechanical energy. So the GPE at B plus the KE at B has to equal the GPE at A plus the KE at A. So mass times 9.8 times 30 plus 1/2 m times 12.1 squared equals mass times 9.8 times 35 plus 1/2 m times the velocity at A squared. Cancel out your m's, solve for the velocity at A, and you end up getting 7 meters per second. So that's the velocity that we need at the top of that first hill to get around the loop. Okay? So now, here's the next part of this. So that was the answer to part A. Part B. So it says, in this case, what is Roy's acceleration when he's at 3 o'clock on the loop? All right, so let me clear my screen here. So what we're trying to figure out here is when Roy gets to this point right here. Oh, that wouldn't be 3 o'clock. Oh, shoot. That would be 9 o'clock, wouldn't it? So if you imagine our loop being a clock face, then you'd have 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. So 3 o'clock is over here. It wants to find the acceleration there. Now, you got to be careful because there are 2 types of acceleration at that point on the loop. So let's go down. I want to make a new drawing again. So here's the loop. So when you get to this point, there are 2 types of acceleration. Namely, he's going in a circle, so there's going to be centripetal acceleration, And he's moving downwards, which means we're also going to have tangential acceleration. In other words, he's going to be speeding up. Okay, so now we're going back to our non-uniform circular motion, right? This centripetal acceleration is going to be v squared over r, okay? And our tangential acceleration is going to be a result of our vertical forces. So maybe we need to make a new drawing like this, but one with forces on it, so we can kind of figure out a little bit better what's going on. So let's go and make the same drawing again, but this time I'm going to do it with forces. So here's my loop-de-loop. Here's Roy. So when he gets to that point, what forces on him? What forces are on him, right? Well, gravity is pulling him down, and there also has to be a centripetal force pushing him inwards. That's going to be provided by the normal force from the seat that he's sitting on. Okay, so it looks like the normal force will be mass times centripetal acceleration, because that's the only centripetal force. All right, and then gravity is my only tangential force. Okay, so gravity is causing him to speed up. The normal force, the seat pushing his butt, is providing that normal force to give the centripetal force. So tangential acceleration is going to be g. Centripetal acceleration is going to be v squared over r. So we need to find the velocity at that point. So let's see. So what's going on? So we already know at this point, point B, we know the height is 30 and the velocity is 12.1 meters per second. We'd found that before. So now what we got to know is over here at point C, the height is going to be 15 meters, right? Because the radius is 15. And we got to find the velocity at point C, right? So that we can find our centripetal force. I'm wishing I'd drawn a Latin blue. Oh, you know what? I think I can still do that. Look at me. Haha. All right. So what we're going to do is we're going to use conservation of energy, exactly the same as we did before, right? We got one point where we know the height and the velocity, and the other point where we know the height. So you're going to use conservation of energy. Use conservation of energy. And when you do that, you'll find that the velocity at point C turns out to be, on the next page of my notes, I think it's 21 meters a second. Weirdly, I think the math worked out really nicely on this one. Yeah, 21 meters a second. So now we can find our centripetal acceleration. It's going to be, oh, shoot. I shouldn't have used point C because that's, I guess it doesn't matter. Whatever. All right, so our centripetal acceleration at point C is the velocity at point C squared over radius. So 21 squared over our velocity, or over our radius. And you'll find that the centripetal acceleration turns out to be 29.4 meters per second squared. So when he's at that point, here's what we got going on. We have a centripetal acceleration of 29.4 meters per second squared. We've got tangential acceleration of 9.8 meters per second squared. And so now we just do vector addition to find the overall acceleration. So AC, AT, here's our acceleration. So go through and do the Pythagorean theorem, and you will get 31 meters per second squared. And I guess if you wanted to, you could find this angle, which I don't know off the top of my head, but you could definitely figure it out, right? And it would be, what, 31 meters per second at some number of degrees, I don't know, below the horizontal, however you want to write that. Okay, but the point is, there are two types of acceleration. You're speeding up, so you've got tangential acceleration, and there's centripetal acceleration to deal with. All right, I am wishing I'd poured myself a cup of water. We have one last example to do. All right, this last one is super important. All right, I can't stress this enough. So if you need to, pause the video right now, go get yourself a drink of water, and then come back to this. All right. So it's quick though. Here we go. All right. So everything that we've done so far, we've said that the total mechanical energy at this point equals the total mechanical energy at this point. Okay. Often what is useful is to do the following. All right. So suppose I say that the total energy, I gotta get better about mechanical. Okay. The mechanical energy at point A is equal to the mechanical energy at point B. If I subtract mechanical energy, better yet, here, let's even do this. My initial mechanical energy equals my final mechanical energy, right? Where point A is initial, B is final. So if I subtract initial from both sides, then I get this. Right? My final mechanical energy minus my initial mechanical energy is 0 because they're equal. Oh, that means my change in mechanical energy is 0. Okay. This is going to provide us a super secret ninja shortcut on how to solve these problems. Okay. It is often easier to figure out how much your energy changes. All right. So what do we mean when we say change in mechanical energy? Well, change in mechanical energy is just your change in kinetic energy plus your change in potential energy. Okay, whether it's elastic or, we'll list them out separate. Oops. I'm sorry this video is so long, you guys. This is one of those sections where I couldn't break it up into smaller bits. Okay, cool. So, and remember, change is always final minus initial. So let's write out what each of these are. So, change in kinetic energy. So that's kinetic energy final minus kinetic energy initial. That's 1/2 m times Vf squared minus 1/2 m times Vi squared, which is 1/2 m times Vf squared minus Vi squared. Okay? Notice, this is not the same as this. Okay? You can't find your change in velocity and square it. You have to square your final velocity, square your initial velocity, and find the difference between those. Please, please, please watch out for that. Okay? So here's my equation for change in kinetic energy. That is important, so I'm going to highlight it using yellow. Okay? So that's change in kinetic energy. Okay? Let's do GPE. Oops. Or no, let's do EPE. No, EPE. Let's do EPE. So change in EPE is almost the exact same thing, except instead of 1/2 mv squared, it's 1/2 kx squared. So I'm going to just go ahead and write out what you get for that. Change in EPE turns out to be 1/2 k times final x squared minus initial x squared. Okay, again, super important. All right. I'm not going to highlight it in yellow because it takes too long to switch to the highlighter. All right. Finally, what about change in GPE? So this is the one that I want to point out. This one is actually the easy one. It's the one that this is going to make your life easier. And right now you're watching it and you're going, I get it. Please bear with me. This is going somewhere. All right. So this would be GPE final minus GPE initial. Oh no, my new pen is being a poop. All right, which is mg height final minus mg height initial, which is mg times height final minus height initial, which is mg delta h. So a lot of times we run into those problems, right, where we're like, I don't know what point I want to call a height a 0. It doesn't matter. All we care about is how much the height changes. Okay? I cannot understate how important this is. Change in GPE is mg delta h. Cool? All right, so why do we care? This next example will show you why. All right. I use this often where I'll set my, instead of setting total energy here equal to total energy here, I'll just say the change in total energy is 0. Okay. Change in KE plus change in GPE plus change in EPE all adds up to 0. All right. So let me show you. Here's a perfect example of when this really matters. All right. So here we've got this system. So I've got a frictionless surface with two blocks on it. There's a block, well, one block, a block of mass 3m on it, and then there's a rope with a pulley, and a block of 2m is dangling from it. All right, and it's going to be released from rest. So our initial velocity is 0, and the question wants to know what's the velocity of the boxes. They're tied together, so they're going to move together. When this guy has moved down 0.4 meters. Okay, so, oh darn it. Okay, darn it. So what do we do? So what are our forces? Well, there's gravity, normal force. Gravity's conservative. Excuse me, normal force doesn't do work because it's perpendicular to the motion, right? Gravity, normal force. Tension's internal. So I think that's it. Sorry, barky dog. So anyway, long story short, our total energy is going to stay the same. Or for us, our change in mechanical energy is 0. And that's how I'm going to approach this. So our change in mechanical energy is 0. So that means our change in gravitational potential energy plus our change in kinetic energy is 0. So I think we need to be more specific though, right? Because which objects are going to undergo a change in GPE? Well, this guy's going to move horizontally. So it's going to have a change in GPE of 0. This guy is going to go down. Oh, that's going to lose GPE. So this is really the change in GPE of the 2m block plus the change in kinetic energy. Well, let's see which objects have, oh, they're both going to be moving. So both blocks have kinetic energy. So this is the change in kinetic energy of the 2 and 3m block. And these all have to add up to 0. Okay, so the change in GPE for the 2m block, well, that's m times 2m, sorry, 2m times g times our change in height, which is negative 0.4 meters. Notice, oh my goodness, notice the change in height is negative because it is going down. Okay, so that's my change in GPE. Okay, plus my change in kinetic energy, which is KE final. Let's see, 1/2 times, oh, well, the total mass is 5m because both the 2m and the 3m are moving, times final velocity squared, minus, well, my initial kinetic energy is 0. All right, and this all has to add up to 0. Oh, I was so excited about this new pen, and it's totally being annoying. All right, so what are we going to get here? 2 times 0.4 is 9.8. So I've got negative 7.84 m plus 2.5 m Vf squared equals 0. So now we just got to algebra this. I'm going to move the 7.4 over to the other side. So I've got 2.5, oh, and divide by m. So 2.5 Vf squared equals 7.84. And then solve this. And the reason I hesitated for a minute is, oh shoot. The reason I hesitated is when I did my work, I made my change in height 0.4 meters. So you're just gonna have to wait, and I'm sorry. Oh my goodness. So I suppose I could have done this in my head. All clear. 7.84 divided by 2.5. So we get VF squared equals 3.136. Take the square root of both sides, and you get VF is 1.77 meters per second. All right. So, but the thing that I think I did not do a great job illustrating here is this. Check it out. People always get tangled up on this because the problem doesn't tell you the height of the table, right? And it doesn't tell you the starting height of this 2m block. So it's weird, right? Because you don't know the height at individual points. But what we do know is the change in height for both blocks. 0 for this guy and negative 0.4 for that guy. All right. If you have a system of multiple objects, I strongly, strongly recommend that you use this method to solve the problem. Okay. That's it. Cool. Long video. I'm sorry. A lot of information there.